last part of, oh no, part C. Nope, yeah, last part of the exam. So now we have a conductor inside the two plates. So it says now the interior charge sheets are removed and are replaced by a conducting metal plate with zero net charge. So again, we have to plot the x component of the electric field and the electric potential. And the potential is defined to be 0 at x equals 0 and a positive value, so same stuff, positive value for Ex means that the field points to the right. Okay, what we know about a conductor is that the field inside it is 0. So the electric field inside this conductor is 0. And the way that that's going to happen is that charge is going to build up. So negative charge will move towards this plate, and positive charge will move towards this plate. And then what you'll get is when you get a positive charge sheet over here and a negative charge sheet over here, then these two fields, the fields due to these two sheets will cancel out here and will cancel out here, and the field due to these two sheets will cancel everywhere too. So we'll have 0 out here, 0 out here, and 0 in the middle. But the field inside these two regions, they will point again in the negative direction this way and in the negative direction this way. Okay, so we had on this side 0 field, then it goes up, then in the conductor it's 0 again, it's back up to a constant, and then it's 0 again on the outside beyond this charge sheet. So this constant here is E equals, and we have our charge density is 30 nanocoulombs per meter squared along this plate, and that's what will also build up along this plate in order to cancel the field on the inside here. So E equals sigma over epsilon naught, which is 30 nanocoulombs per meter squared over epsilon naught. And this is pointing to the right. So calculate the electric field strength at x equals 1.5 centimeters on the x-axis at the center of the solid metal plate, and the electric potential difference, delta V. So let's draw the potential first, actually. So again, it's a constant out here where the field is 0, and a constant here, so it's a constant inside here. And this electric field's pointing to the right towards this negative charge, and so we're going to have a linear drop in these regions. So our electric field is going to look like constant, constant, it'll drop, be constant again, drop, and be constant again. Okay, and he defined this to be at 0, so this is going to go down some amount. So we know that at x equals 1.5 centimeters, somewhere in here, then we're going to be at this point here on the potential, and so we need to find what this is, right here. This drop, and that will be our potential. So the electric potential is the work it takes to move a positive charge to that point from 0. So if we were here and moved a charge down to here, we could find the work done, and the work done per charge. And so that is the electric field times the distance. And that's the electric field 0 out here, so that's just 0. And then inside here, we have this constant electric field that we found, and then times the distance that we spent in there. So from here to here is 1 centimeter. So the work, this is work per charge, is electric field times distance, which is 30 nanocoulombs per meter squared over epsilon naught, times the distance that we would move this charge, which is 1 centimeter, 0.01 meters. Okay, and this is, so the solution would be negative 33.88 volts. And you know it's negative because you've moved the particle out from 0 to some place with the field. So this is the direction it would move. It would have moved naturally, so it went down in potential. So this was the answer here, 33.88 volts. And the electric field at that point, it was inside the conductor, so the electric field would be 0. And that's in volts per meter.